Hello, everyone. This is Sujaya, and today now we're going to shift some gear and look at cloud-based security. In this talk, I'm going to talk about how we built a fault-tolerant Oblivious data store. Because we're already at the security conference, I don't need to emphasize the importance of data privacy. When we think of data privacy, the first obvious solution is to encrypt the data. Here, I have a toy example of a pharmaceutical company that produces 4 different types of medicine. And so this company encrypts this data and stores this data on some third-party cloud provider that may not necessarily be trustworthy. We're specifically looking at honest but curious adversaries that are not going to actively manipulate my data, but will passively observe and learn some non-trivial information about the system. Researchers have shown that just encryption is not enough to preserve data privacy. And here is a very simple attack where I have the encrypted medicine data stored on the cloud, and I have clients buying medicine and hence interacting with this data. Over time, the adversary learns the access patterns, learning what percent of the time which row is accessed. Now, another pharmaceutical company, completely independent of this, produces its yearly sales statistics. The adversary, having access to both its model and the public knowledge, can map the two. And next time when a client accesses row number 4, it guesses with high probability that client is buying medicine for breast cancer. Such kinds of attacks are called access pattern attacks. And in fact, there have been a large number of works that show the practicality of such attacks. Oblivious RAM, or ORAM, is a cryptographic technique that mitigates access pattern attacks. The core idea in ORAM-based data stores is to make the accesses to the external server look completely random. And a typical ORAM data store has this kind of architecture, where there is an untrusted storage server that stores the encrypted data. There is a trusted proxy that stores encryption key and other metadata. And the adversary typically controls all of the communication channels in the system. To give you an intuition on how ORAM solutions hide access pattern, I'm going to explain one of the really well-known protocols, Path ORAM, at a very high level. Path ORAM constructs its data on the external server in a binary tree structure. And when a client wants to access, say, this particular orange block of data, Path ORAM reads the entire path of the data in the first step. And in the second step, it randomly shuffles the physical location and writes that shuffled location back to the server. So essentially, after each access, orange block's physical location is being randomly shuffled. And this is how ORAM solutions hide the access patterns. Having given this high-level overview, let me now discuss the issue with existing ORAM solutions in that they are not fault-tolerant. If my external server crashes, of course, that's where my data is, so I lose access to all of my data. But even if the proxy crashes, because that is where the encryption key is stored, I still cannot access my data. So essentially, if either of these entities crash, the application ends up losing access to all of its data. I want to take a quick note to mention Abbadi, which is a recent work that provides data durability guarantees, but it doesn't give liveness in that while the proxy is down, the application cannot access any data. So given the issue with the solutions, in our work, we propose QuORAM, which is the first fault-tolerant and replicated ORAM data store, which uses a quorum-based replication protocol. QuORAM system and threat model looks like this. Because if the server or the proxy crashes, I lose access to data, we bucket them together in a single unit and replicate the data across n such units. And the clients have an all-to-all communication with the proxies in the system. To tolerate F crash failures, QuORAM replicates the data across 2 F+1 replicas, and it tolerates honest but curious adversaries that can control all of the storage servers as well as the communication channels in the system. Having given the system and threat model, let me now define the 3 goals that we want QuORAM to achieve. At its core, it is an oblivious data store, so we want it to hide access patterns. We want it to be fault-tolerant, so we want it to replicate the data, and we want it to provide linearizable semantics. What linearizability states is if I take a single data item that has many read-write operations on it, From an external observer, these operations must appear linear. So in describing how we achieve these three goals, let me first focus on the replication protocol and linearizability. So I'm going to first take an efficient existing solution in designing QuORAM, solutions such as Hermes and Crack that are read optimized, in that when a client wants to read the data, it reads from a single replica. When it wants to write the data, it writes to all the replicas. So we see that this is read optimized. Now, we cannot use such a system in developing oblivious data stores because just the number of message exchanges between the client and the server reveals the type of operation the client is performing. So this is not oblivious. So what we need is a solution that accesses the same number of replicas for both read and write operations. And so let this be the second solution, where read operations access a majority and write operations access a majority of the replicas. Now, to see the issue with this solution, let's take an example where all three units store an item X whose value is 5. I have one client performing a read on a majority, 1 and 2. The first message goes through fine, and it gets updated. The second message is still on its way. Now, at this precise point, another client performs 2 consecutive reads. First, from units 1 and 2, it learns the value of X to be 10. Next, it reads from units 2 and 3 and learns the value of X to be 5. So what is the value of X? From this client's perspective, the read and write operations are non-linearizable. To make the solution linearizable, we either need locking, but locking in distributed systems, if there are deadlocks, we need extra communication, and so that will not be secure. And so what we do is we add another round of communication to order the client requests. And so let me now discuss QuORAM's replication solution, which is inspired by Lynch and Schwartzman's solution. We have every data item in QuORAM has a value v and an associated tag t, which is a monotonically increasing entity. We can think of this as timestamp-based data stores. And the replication protocol is executed in 2 rounds, the query and the propagate phase, which looks like this. The client that is interested in reading or writing the data drives the execution of the protocol by first sending an ORAM read request to all of the replicas, waits to receive a response from a majority, and for read request, it picks the value corresponding to the highest tag that is received, and for write request, it updates both the tag and the value, and for either requests, it sends an ORAM write request, and when it receives an acknowledgement from a majority, its operation is successful. So this is how the replication protocol achieves both lock-free behavior and provides linearizability. Now, let me go and discuss how do we hide the access pattern in QuORAM. And for this, we use the underlying ORAM scheme, which is tau ORAM. This extends path ORAM that we saw earlier, but includes concurrent and asynchronous requests. Now, if we use tau ORAM as it is in QuORAM, we end up double fetching the path. For every client request, a proxy will fetch the same block twice. To see why this is the case, let's recall that QuORAM's replication happens in 2 rounds. In the first round, when a client sends an ORAM read request to a proxy, an unmodified ORAM would read and write the data for this request. And when a client sends the corresponding ORAM write request, a proxy again will read and write the data, essentially incurring 4 rounds of communication, 2 of which are completely unnecessary. To mitigate this inefficiency, QuORAM meticulously keeps track of the ongoing client request by introducing a new data structure called incomplete cache map, where this incomplete cache map stores the requests that have finished the query phase but have not yet finished the propagate phase, essentially ongoing requests. And to see how this helps us mitigate the double fetching, let's go back to our example where a client sends an ORAM read request for which the proxy adds this request to the incomplete cache map and only performs the read operation. And in the second step, when it receives the ORAM write request, it checks for this entry, removes it, and then performs the write operation. Oops. So hopefully this gave you an intuition on how do we achieve replication as well as hide the access pattern. Now let me discuss our performance evaluations. We evaluated QuORAM with 3 baselines. First is the insecure but fault-tolerant baseline. Second is secure but not fault-tolerant, so there is no replication in this. And third is secure and fault-tolerant, where we use Obladi's approach of relying on the cloud itself for fault tolerance. And for that, we use an open source database, CockroachDB. We place 3 replicas on 3 different geographical locations on AWS, and we use YCSB benchmarking. In this talk, I'm only going to discuss throughput results. These are the throughput values for QuORAM, and in comparison, these are the throughput values for the insecure baseline. And we see the counterintuitive result that both these performances are very similar to each other. And the reason for this is when we have geo-distributed replicas, the cost of communication is significantly higher than the latency to achieve obliviousness. And because of this, both insecure and QuORAM performs very similar to each other. Looking at the no replication, secure but non-fault-tolerant solution, we see that this is about 2.4 times worse than QuORAM. The reason for this is this has a single proxy, which is being overloaded. And when we have geo-distributed clients, they face extremely long latency communicating with a single proxy, which translates to low throughput. And finally, looking at the CockroachDB baseline, this is about 33 times worse. And the reason for this is this also has the single proxy bottleneck. And the second reason is its replication protocol is leader-based. So one node is serializing all the requests. So these two causes the bottleneck, which leads to its low performance. We have many other interesting results in the paper, and I encourage you to take a look at it. So in concluding this talk, I presented QuORAM, which is the first fault-tolerant oblivious data store, which hides the access pattern, replicates the data for fault tolerance, and has significantly better performance than the baselines. I want to take a quick minute to dedicate this work to the loving memories of Caitlin Scarberry. She was a BSMS student at UC Santa Barbara, and this project originated as part of her master's project. And her inputs in this work have been valuable. Her loss is immense to all of us and the research community. I will take any questions now.